to get real data and be able to answer some of these incredible questions that we've got. Fascinating stuff from this time, but more to come. Dwayne, I turn it back to you.
Thank you, Marilyn, and our scientists. Okay, now it's time for our question and answer period, and we are going to start here at NASA's headquarters. Please wait for the mic and give your name and affiliation.
Seth Borenstein, Associated Press. Okay. For Dr. Zuber, can you sort of give us a time frame of the volcanic eruptions we've seen? One, how surprised? I mean, you said you didn't think early from Mariner data, you didn't have much of, it was still up to debate on how much volcanic activity there was. Can you tell us about how long ago the volcanic activity was and sort of give us a good sense into the amount of volcanic activity, overall the whole planet? I mean, are we looking at just tiny hotspots overall, or half the planet at any given, during the heyday, we're in the process of erupting, cooling, or some kind of volcanic activity?
Okay. Well, Mercury is the smallest of the terrestrial planets, and with planetary bodies, they tend to take a while to heat up, but then they cool off pretty quickly. So the planet like Earth, which is the largest terrestrial planet, is still very active today. Okay, but the smaller terrestrial planets like Mercury and the Moon also falls into that category. Most of the action, we think, happened in the very earliest history. Okay, and we don't know the absolute date of that because we have not been able to sample the rocks. But when we think about that, we think on the order of 3.8, 3.9, 4 billion years ago, where Mercury accreted about 4.5 billion years ago. So this was really in the very formative stages of the planet. Although it's possible, because Mercury has a large iron core, that volcanic processes could have continued much farther into time. But the preponderance of activity probably happened early. And then when you think about how much there is and where it's at, well, we really need to analyze Mercury once we get into orbit in order to do a global inventory of that. So it's not really possible to say. But with Mercury that has a core that's 75% of the radius of the planet, there's some thought that cooling off of the core and the processes associated with convection in the core, which helps it cool off, that heat released from the core then heated the mantle, which heated the crust, and so that there, one would expect, more of a global distribution of activity, but that's a hypothesis that we're going to have to test when we analyze data from the entire planet, as opposed to just from the limited amount that we analyzed here from this flyby.
Mark, would you have anything to add based on smooth plains?
I'll add a little bit to that. It's a very good question. And on the first flyby, we saw finally the full extent of the Chloris Basin, which we had seen about 20 or 25% of it. It was right on the terminator from the Mariner 10 data. And one of the beautiful results from that messenger view of Chloris Basin is that the basin is predominantly filled with these smooth plains deposits. And the diameter of the basin is something like 1,400 kilometers. So there's something on the order of 1.5 million square kilometers in one smooth plains deposit. And from Mariner 10, we saw, as it was disappearing over the North Pole, the edges of some very large smooth plains deposits. And these flybys aren't optimal for looking at the poles. As you can see in that coverage map, they kind of get cut off. But we're seeing hints that from the two messenger flybys that this North Polar region has a lot of these smooth plains deposits. And then I think that one of the key messages that's coming out of the analysis of the M1 and M2 data from the volcanologic standpoint is that these volcanic deposits, lavas came to the surface, they cover a lot of the surface. And Maria made an excellent point that we'll really have a hard number on that after we've analyzed these data and we go into orbit and cover the whole planet in a much higher resolution. But the bottom line is volcanism was very important in the history of Mercury.
I guess just to follow up, it's fair to say it's more than you expect. Is it fair to say it's more than you expected going into this flyby?
Well, it was more. Maria hinted at this debate that's been going on since the Mariner 10 days. That how it is in science. There's always arguments, right? Some folks had thought that the volcanism was extensive on Mercury, and others were very much more cautious and thought that maybe these smooth plains deposits were actually impact ejecta from big basins. So depending on which side of the fence you're on, you could answer yes or no on that. And Mariner 10 took place when all of us were in junior high school, so I'm not going to really say who was right or wrong. Right?
But this shows that it's tips the theory more into the concept of it was more volcanism than ejecta. Correct?
Absolutely, absolutely.
To add to that, it shows that there's a lot more volcanism than we see on the surface of the moon, which has always been the planetary body we compared Mercury to.
So, my name is Loretta Whitesides with Wired Science. Maria, you talked about the wrinkle ridges on Mercury being twice as high as the ones on Mars.
Just one.
Just okay, so one of the ones. So it was twice as high as one particular one on Mars?
No, thousands.
The average.
Okay, on Mars, in middle Martian history, there are vast volcanic, frozen out volcanic deposits on the surface of Mars that contain just abundant wrinkle ridges there, and those ridges have a relief. And we've measured thousands of relief measurements from the Martian data because we have global data. Those go from like 80 meters to 300 meters, okay, in terms of relief. And here the one that we've measured is 600 meters, which is very significant. And so if that is going to scale up, it would suggest that the amount of contraction in Mercury is very substantial. But one doesn't want to make an extrapolation about the whole planet on the basis of a very limited data set. But it certainly does cause one's imagination to think about what the possibilities are here.
Is that something that you would have expected to see on Mercury, that they would be bigger for any reason?
It depends somewhat on the properties of the crust and basically how deformation of the crust is taken up. So there are different ways to deform the crust. There's what we call a penetrative deformation, where the crust just cools off and contracts without any faulting at all, and it might fold, for example. Okay, or faulting could take place, but it could occur on lots of little faults, in which case you would see a very small elevation offset, or you could see a great deal of fault slip taking place on just a small number of faults. Okay, and so which one of those happened depends on what the properties of the crust were at the time when the stresses were accumulating, and what the mechanism of the stress is, whether it's a global cooling or something else. So so we have there is an analogous situation on Mars where this is the ridges are contractional, but on Mars we have extensional features called graben, and there are places on Mars where you have lots of little graben, and then you have the Valles Marineris, which is 250 kilometers across and 8 kilometers deep. So something unusual about Mars caused a big crack in one place and lots of little cracks in another place. And so we really need to do a more global inventory of Mercury to start making measurements of these features.
Do you have any other questions? Seth, did you want another follow-up?
Just to follow Seth Borenstein, AP again, just to follow up on. So overall, I mean, is it fair to say that each time you've gone back to Mercury, I mean, this is, I guess, twice. Yeah, it depends on how you count the first.
Right.
That it's showing that it's a lot more. It was a lot more dynamic than theory shows. I mean, between the